Now I will tell you something about the calculation time. Look for the replacement block system, the step depth estimation we have covered, the sample and hold block we have covered, and now I have to tell you something about what we have to do with the calculation time. This is chapter 6.7.3. Calculation plus conversion time. Also the analog to digital, also the digital to analog converter needs some time before the computer can work on. Of course, this appears in our analog system as a delay time block. We call this TC from calculation, but includes conversion time. The question is, if I design the controller, how large is this calculation time? So this is the next step. I want to give you some methods to find out in your system how large is this time in your system. Methods to get value of TC. And in total, I will tell you 4 methods. First, of course, you can look into data sheets of analog to digital converter or digital to analog converter. You can find out how many microseconds it takes to sample a value and put this into the computer. For the calculation time, we can look how long takes a multiplication. We need 3 multiplications for a PID, so this could be a step to find out theoretically information. Theoretical information. But this is rather time consuming. You need many steps to get good estimations of TC, and that is normally not the way we want to do this. But the only way which can be done if the hardware at this time of development point is not available, then you cannot measure it. But if the hardware is available, this is the second point, you can measure it. Measure with existing hardware. How can you measure the calculation and conversion time? 3 methods. Use stopwatch. You may remember this class in C# where internal in the computer and very fast counted counter is used to measure the difference time between 2 time points within the resolution less than microseconds. That could be a software stopwatch or a hardware stopwatch in your hand. Write the software for your controller, put it into a loop, say do this 10,000 times, and then take a manual stopwatch, measure the running time, divide your result by 10,000, and then you have the average time of your control loop system. So use stopwatch, that is a direct measurement, or there's B, use a second output. To produce a pulse. How does this work? Let's have a look into the description of the controller software routine. A view into the paper. Stop. which on page 13 in our paper you see this block diagram, and the box internal of the box, the big box, it describes what you have to do in each step. So here ADC, calculation, DIC, actualization. That is what you have to do in any step. So if you want to know the time point from there to there, so the duration including ADC, calculation and DIC, the idea is make with the command at this time point, before you start, switch your second output, either digital or analog, to 1 or to 1 volt or so. Do your job here, and then after finishing actualization, switch back to 0 volt. Then you get an impulse which looks like this, result of pulse before ADC 1 volt, after actualizing, put it to 0 volt. Then if you have a scope, put your input of the scope to this output of your second output, and then you see a pulse, a periodical pulse, where the period is your sampling time and where the pulse duration is a good estimation of the calculation time. Of course, this increases the time a little bit because DIC has also some time, but normally the DIC setting goes very fast. So this is a good way to measure the sampling time. You have seen this in the Control System 1 lab in the experiment 2. We have done this already. Okay, third thing is, if you remember, sample and hold should be replaced in our situation with the half of the sampling time, the sample and hold block. And now your delay time of the calculation conversion time comes additionally to this. This in total gives, if you add, if you have a series connection of 2 delay times, this leads to a new delay time block, gain all is 1, with the sum of this delay time. So this is TC plus half of sampling time. So if you have an indication that TC is very small compared with the half of your sampling time, say you have a slow system and sampling time is 1 second, and you know your microprocessor system leads not more than for calculation and conversion 1 millisecond, then if TC is very small compared with T0 halbe, neglect it. If the ratio between both is very large, TC is very small, then you can neglect it, and because then the delay time of the sample and hold block is dominating and influence your control loop, and your sampling time is known, and then you can of course very good calculate, design your loop. And there is a fourth method where you do the following. I call this use the real algorithm. Use the real algorithm, that's my name, instead of ideal algorithm. what is this? The idea is very simple. We enlarge the calculation time to artificial, well-known new time. So we wait with the storing of the DAC. We don't do this here in the after calculation. We shift this output command to a position where we know exactly how long this takes, and the best idea is do the output at the beginning before you make ADC. So you make an output of the value you have calculated in one step before, and then the calculation and conversion time doesn't depend on the hardware, but is exactly known as complete sampling time. This is described on a page deeper in my paper. In this chapter 6.7.3, and here you can see what I mean. In the ideal algorithm, you make it as fast as possible. In the real algorithm, you shift just the order of the commands in that way that the output of the DAC is done before you calculate the new value. That means yn is then the value you have calculated one step before. This enlarges the calculation time to one complete sampling time. Enlarge the calculation time to a complete sampling time. So in other words, look at picture, top page. Was war das for the page? That is page 20. The consequence is TC then is a complete sampling time, so larger than possible, but hardware independent. Larger than possible. That is a consequence is controller will be slower as necessary. That's a disadvantage, but independent of hardware. You are independent of hardware, and you can start your controller design before the hardware is developed or measured, or independent of all things. The only thing, of course, is your calculation time should not be larger than sampling time. Of course, then the system doesn't work. Yeah, but if this is smaller than this, set it TC to sampling time. Now this is a very simple step, and then finally the delay time. Total delay of digital PID is TC is one sampling time plus, of course, the sample and hold part is a half of the sampling time, so this is 1.5 times sampling time. That sometimes this is for didactical use in our lab. We do this because then we are independent of which computer in this moment is used, which ADC card is used. We are absolutely independent of hardware, and this works since years without any change of the design. So now come to a conclusion. If we know that we want to run our PID on a digital system, then replace the PID in the FRA design with the following block in the FRA design with a PIDT1, design a PIDT1 with the KC, with the TN, with the TV, and with the step depths. And add a delay time block. These both things you have to do, and the delay time block is again 1, and the delay TC plus sampling time divided by 2. And the step depths of the PID depends directly on the sampling time. If you know the differentiating time constant of our PID, you can then directly calculate the sampling time of the system. This is described as a step-by-step procedure in a page you can find in my paper, and this is this block on page 20. Let's have a quick look on this block. You have to know the procedure of the FRA design of control system 1 lecture. There are some changes. I will explain these changes. That's just a repetition of that what we have done in the last minutes. First step, which is new of digital systems, decide for a sampling time. Yeah, that is what you have to do before you can start the design. You have to find out for your hardware which is the appropriate sampling time. If this is defined, then add to your process the delay time block with just a delay time, half of sampling time plus calculation time, whereby TC represents the calculation time including conversion time, of course. In the real algorithm, if you decide for using the real algorithm, the calculation time is just 1 sampling time. Note that the delay phase can be calculated, but normally in the your simulation program or in Rec C# or so, it's automatically done. Yeah. So add a delay time block. Now, point 3 is if you want to have a D part. Now, the step-by-step procedure of a PIDT1 controller starts with the PDT1 and then works with the PI. Yeah, that is the well-known method of the FRA design. So if you want to have a differentiating and acceleration of your loop, you have to find out the TV value. Take pole compensation or minus 30 dB method or any other way to find out a good TV value. If this is known with the known sampling time and this TV value, you just calculate the step depths of your PIDT1 controller, and then you can add the phase of the PDT1 part to the process phase. This gives process is VS, here called VS, plus delay time plus our PDT1 block phase. This gives a new phase curve, and now with this new phase curve you can make the standard FRA design, which you can find in workbook control system 1 page 37. Unchanged design point here. All things for the digital controller is covered. If you are ready with the design, then you have found a KR or KC value, a TN value, TV value is just coming out of these. Here's step number 3. Then you can convert into the summing form, get your K, your TI, your TD, and then you can calculate your 3 Qs, program it, run it, and be happy, because then you get a very nice controller type. I want to close this this point, this chapter 6 design method of a PID, of a digital PID controller, with an example. This example is demonstrated in a new video. Yeah. Thank you. Start with a new video.